Okay, so what we're going to do now is we're going to use equilibrium calculations to figure out pH of weak acids to weak bases. And there are basically two kinds of react calculations. You're going to be figuring out Ka or Kb given concentrations, or the other way around, you'll be figuring out concentrations using Ka or Kb. First thing we're going to do is we talk about this in equilibrium, is first of all, I want to make sure that which way the reaction it goes, and so what we have to do is figure out Q. And if Q is too big, that means the reaction will move to the left, and you got to make the appropriate changes. And if it's less than K, then the reaction will move to right, and you have to make the appropriate changes there. But we won't have any problems like that. And like I just said, you'll either be given a pH, initial concentration, or you'll be given K. And so let's do problems. So the first problem is you're going to be figuring the Ka for nicotinic acid, niacin, which I think is vitamin B3. It's monoprotic acid. That means it just gives off one H. And it has a concentration of 0.012 molar with a pH of 3.39. Now this is going to be important because this tells you how much H plus you have. So that will tell you this amount right here. So we're going to set up an ice table and come up with our answers. Okay, so here's the ice table, and here's the equilibrium expression, product over reactant. Here's concentration 0.02, 1, 2, 0, 0, and it changes by X, and this increases by X, and this by X, and so forth. Okay. Now, the key thing here is that we actually know this X right here, and that's the pH of the solution. So the solution is pH is 3.39. We were told that. So that's going to tell us this value here. So what we do to figure this value here is we take the anti-log, or 10 to the minus 3.39, and figure that value out. And that number will go right here, here, and here. Okay, so we put the value there, and what it tells us is how much it's been changed. So this has been changed this much, 0 to this much, so it's been changed by this much. And because there's a one-to-one relationship in the stoichiometry, so that if there's one of these, there has to be one of these and one of these. So this goes down by this value, and this goes up. And then you do this simple math, and this is what you get. So at equilibrium, this is the concentrations of the each species in the solution. And now what we can do is simply use the Ka, product over reactant, to come up with our answer. Now, okay, so one of the things we're going to do is X turns out to be a very, very small number. And what we're going to do is make kind of an approximation here. And it's a good approximation, especially if you use sig figs. Is that if this number here, the Ka, all right, is 100 times or more less than this number here, then you can assume that this has no influence on this value here. Okay. Because this would be so tiny, it would hardly change this value at all. And so you can see that this value here is 100 times or more less than this. It's about 1,000 times. And so what we can do is ignore X here, but not up here because it's not added to anything. So you have X squared equals 0.012, and you solve it, and you get Ka equals 1.4 times 10 to the minus fifth. And the pKa is the minus log. All right. All right. These kinds of problems we're going to be always we're going to talk these related to weak acids, weak base, or both. And the both we're going to talk about these two now, and leave this when we talk about buffers. And there's just a sort of flow chart. I'm kind of skip that for now. And okay, let's do another problem. So let's say I have hypochlorous acid. It's a weak acid with a Ka of 3.0 times 10 to the minus 8. What I want to do is find out the pH of solution when it has initial concentration 0.2. So what you're going to do is you're going to set up an ice table, and then use this information and this information to figure out your H. So this one's different than the previous one. This one, in the last problem you were given pH and initial concentration, you could figure out Ka. This one, what you're doing is that you're going to be using Ka and initial to figure out pH. Okay, but when you set up the table, hopefully you'll see how it works. All right. So here's the table. Here's the reaction. And so you start with 0.2 molar and 0 and 0. And so so you lose X, gain X, and gain X. Again, that's because there's a 1 in front of here. If there was a 2, you'd have to put a 2 here. But and then the equilibrium is 0.2 minus X, X, and X. Okay. So you know this, so you know K, and you know the equilibrium expression. So you plug in X squared over your product. So this is your product of your reactant, and so you have this value equals this. And again, we can ignore this value here because this number is at least 100 times smaller than this value. Right, so we get 3.8 times 10 to the minus 8 equals X squared, and then just solve for X squared, and then you get X, which is this value, but it's right here. Let's figure out pH. So it'll be pH equals minus log of this value, which is 4.11. Okay, now what we're going to do is the same kind of idea, but with a base. So morphine is a drug to relieve pain, and it's a base, and here's its chemical reaction. And you can see that what it does is it produces base and not the conjugate acid. So what we're going to do is so it says we want a pH, but this here, there's no H plus. So what we're going to do is we're going to solve for the OH minus. And then once we know OH minus, there's a couple ways we can find H plus. We can either use OH minus plus H plus equals 10 to the minus 14th, or we could change this into the PO and figure out the pH. So let's set it up. So right now you just run through it, and we're going to use this here value. Set up ice table. Initial value is 0.075, 0, 0. And gain, lose. And so these are your final concentrations. And this is the key one right here. And you can tell they're all X. So you set up the KB. Here's the equation over X squared. And again, we can ignore this X here because it's way smaller than our initial concentration. And then what you can do is you can just solve. So just accept this set this up to the equilibrium constant, and then solve for x, and you get figure out the OH minus. And then what you can do is you can find the PO, and then from the PO you can figure out the pH. All right, if you want, you can turn it off and try to do this one yourself. So you're given, this is methylamine, and has a Kb equal to 4.4 times 10 to the minus fourth. The initial concentration of the methylamine is this, and here's your equation. So what you're going to do is set up an ice table, solve for OH minus, and then from OH minus find H plus. So turn off the PowerPoint and see if you can figure it out on your own. Okay, so here we are. We set up the ice table, and you got initial concentration 0.05, goes down by minus x plus x plus x. Okay, and then what we got, here's our equation, and again what we're going to do is ignore x, and so it's going to be x squared over 0.05 equals 4.4 times 10 to the minus fourth. All right, and then what you do is solve for x, and that will be the OH concentration. Take the PO of that, 2.33, and subtract that from 14. There's your pH. Okay. All right. Sometimes we've been, so far what we've been doing is we've been saying that the change in x is small, and so you don't have to, so you can ignore it. But there comes a point where you just can't ignore it, because the change in x is big enough to actually change the value, this value here. And so let's look at that scenario. Okay, and again, so what we said is that if the acid concentration is greater than 100 times the Ka, then you're okay. But if it's not, then we have to go into a depth, and it's not that hard. It used to be hard because we didn't have calculators, and in equilibrium we saw that we just have a quadratic solver and we can figure things out. So let's go through a problem here. And so I have a pH of 0.15 of dichloroacetic acid, and I want to figure out the pH. Okay, so here's your equation. So you plug it in down here, and your initial is 0.15, going to 0, 0, and so forth. Everything looks the same. So what we're interested in now is this value. Is this going to affect this value? So if this number here, so what we want to do is if this number here is less than 100 times than 0.15, then we have to consider x. Okay. All right. And so, and when we do that, we get, it's not 100 times, it's 3 times. Okay, so we have to keep x in our problem. All right, so we have x here, and so forth. And so now what we have is solving for x squared. if you go back, now what we have is the quadratic equation. Okay, and that's no big deal. You can go through all this, or you just plug it in your calculator and you'll get these numbers here. And you get two numbers because it's squared, and so you're going to be using the positive value, not the negative value. All right. And so x equals 0.0065. And then you simply have this value here will give you your pH, and so it's 1.19. And that's it.